Okay, we're going to be talking about specifically errors and how to calculate type 1 and type 2 errors, but also about validity in questionnaires or experimental tests. So statistical validity can be defined as the extent to which drawn conclusions of a research study can be considered accurate and reliable from a statistical test. Okay? Basically, this is asking, is your survey or test measuring what you claim it is? To achieve statistical validity, it is essential for researchers to have sufficient data and also choose the right statistical approach to analyze that data. There are different types of validity a questionnaire or test can have. It can have content validity, criterion validity, or predictive validity, and you can read those too. You also want to make sure that your test is reliable. A test or other means of collecting data is regarded as reliable if it produces similar results on each occasion it is carried out in similar circumstances. A reliable test is not necessarily a valid one. For example, a test on quadratic equations could be very reliable because students will obtain similar scores each time they take it, but it would not be valid as a test for assessing your ability in a visual arts course. All valid tests have to be reliable themselves and use data from a reliable source. So it is important to test for reliability if you're not sure. One way to do that would be to do a test and then retest. To test that your means of collecting data is reliable, the same test or questionnaire can be given to the same group after a period of time. If it is reliable, there should be a strong correlation between the results on the two occasions the test is taken. So we're looking at a strong correlation, which means that we're doing some type of correlation coefficient. We're calculating some type of correlation coefficient. So you would have two sets of results when doing a test and then a retest. You would have the original results from your test, your first time. So all of these are values, and then you would retest and get other values, ideally very, very similar. So then you would perform a 2-sample t-test. Or a Pearson's correlation coefficient to get an R value. So you'd be looking at whether or not those two, the test and the retest, have a strong correlation. Errors in hypothesis testing. So you do your hypothesis test, whatever test it is, and you want to know whether or not you made an error. And this is something that you can do for your IA. Okay. So a type 1 error is when you reject the null hypothesis when it's true. And we did talk about this briefly when we introduced hypothesis testing in chapter 14, I believe 14.2. But a type 1 error is rejecting your null hypothesis when it is true. So if we're looking at this bell curve, we've got our null hypothesis, our mean here. Say we've got our critical value is down here, critical value. This is the critical region. So when you would reject your null hypothesis and you get a value, statistical value that is in that critical region. So your sample or your test statistic, whatever that is, falls in the critical region, even though your null hypothesis is true. So that means if that happens, you made a type 1 error. And sometimes the type 1 error is not as bad as a type 2 error, but it all depends on your situation. So the way that you calculate a type 1 error depends on the type of distribution you're using. If you're using a normal distribution, you are going to be using the sample distribution that you are given. So this mean that you use is your population mean. And then the standard deviation that you're going to be using comes from the central limit theorem applying to the distribution. And so you're going to calculate this standard deviation by taking the population variance and dividing it by the sample size, right? Normal distributions, remember, include z-tests and t-tests. And remember, there's a lot of different types of t-tests, including a two-sample t-test, even a linear regression t-test. And for all of these normal distributions, getting the probability for making a type 1 error is kind of quick and easy. So remember, a type 1 error is the error that your test statistic is in the critical region, given that your null hypothesis is true. And that's how you calculate this probability for any type of distribution. But for a normal distribution, this is just equal to your significance level, which is very easy to calculate because you're usually just given it. Now for a binomial and a Poisson distributions, you need to find the critical region by using a table. And we've done this before. This is where we would define our binomial or Poisson CDF as a function, create a spreadsheet, and then create a table from that. The critical value is the first value that has a probability or a p-value that is less than your significance level. That is always true. Your critical region depends on your alternate hypothesis, so it's either going to be greater than or equal to your critical value or less than or equal to your critical value. Now, the probability that you're in the critical region, given your null hypothesis is true, depends on what your null hypothesis is. For a binomial distribution, your null hypothesis is whatever your probability of success is. For a Poisson distribution, that is your average rate. Your bounds in your CDF come from your critical region. So we need to first know what that critical region is before we can do this CDF. So this is your critical region. You'll have your critical value as one of your bounds, and then your other will either be 0 or it will be a large number, depending on your alternate hypothesis. The value that you're putting in for your probability of success in a binomial distribution is the value in your null hypothesis. And then for a Poisson distribution is also from your null hypothesis. If you want to reduce a type 1 error, you use a smaller significance level. A type 2 error is accepting or keeping the null hypothesis when it's actually false. So here is your average. It actually comes from your alternate hypothesis or just something else. It is just not equal to your null hypothesis. Let's say here's your critical value and your critical region, and your test statistic is not within it. So your test statistic does not fall in the critical region. It falls in the acceptance region, but it should have fallen in your critical region. So again, depending on the type of distribution, determines how we calculate this type 2 error. So you always want to find the acceptance region first, which is the opposite of your critical region. So we're finding, in this instance, we're finding the probability that you're in the acceptance region when actually the alternative hypothesis is true. So for a normal distribution, for all these distributions, for normal, binomial, and Poisson, you're doing a CDF to calculate this probability. So your boundaries will now come from your acceptance region rather than your critical region. And then your mean and standard deviation for a normal, your probability of success for a binomial, and your average rate for a Poisson all come from your alternate hypothesis. So let's look at an example. Jill and Michelle like to fish. Jill claims that the average number of fish she catches per day is 8. Michelle doubts this and thinks Jill cannot catch many fish per day, so she observes Jill for 1 day. If Jill catches less than 5 fish per day, Michelle will reject Jill's claim. So we first want to state our hypotheses. So our null hypothesis is what Jill claims. So our average, we're just talking about an average here. And our keyword is average number right there. So we're talking about lambda. Lambda equals 8. And Michelle thinks that Jill is not telling the truth. And she thinks that Jill catches less than 8. So the probability of getting a type 1 error is the probability that we're in the critical region given our null hypothesis is true. We're in the critical region when we reject. And it says that Michelle rejects Jill's claim if she catches less than 5 fish a day. So this less than 5 fish, which because we're a Poisson distribution in discrete, that means that we're less than or equal to 4 fish, is the critical region, because that is where we are rejecting. So what we want to do is we want to find the probability that we're in the critical region, so less than or equal to 4, given that our lambda is actually equal to 8. So we're going to do a Poisson CDF where lambda is 8 and our lower bound and upper bound less than or equal to 4. So that means our lower bound is 0 and upper bound is 4. We are just going to do that Poisson distribution, Poisson CDF. Lambda is 8 and we're going 0 to 4. The probability is 0.0996, or about 9.96% of a chance of making a type 1 error. Jill wasn't being honest, and the actual average number of fish she catches per day is 6. Find the probability of a type 2 error. So this is our test statistic. This is what we're going to use for lambda. Okay, so probability that we're doing a type 2 error is the probability that we're in the acceptance region, which is the opposite of the critical region. So our critical region is less than or equal to 4. So the acceptance region is greater than or equal to 5, given we're equal to 6, because that's actually the amount that she catches per day. So this is our acceptance region, which is the opposite of our critical region. And so we're going to do another CDF where lambda is now equal to 6 and our lower bound is 5. Our upper bound is a big number. Not too big though, so maybe like 100. So probability of that is 71.5%. So about a 71.5% that we make a type 2 error in this calculation. So there are some trade-offs between a type 1 and type 2 error, since the error rates influence each other. That's because the significance level, the type 1 error rate, affects statistical power, which inversely is related to the type 2 error rate. And statistical power is determined by a couple things: size of the effect, measurement error, sample size, and significance level. The most important ones are sample size and significance level. So larger sample sizes reduce sampling error and increase power. Increasing our significance level increases the power as well. Now, setting a lower significance level decreases the type 1 error risk, but conversely increases a type 2 error risk. And increasing the power decreases a type 2 error risk, but increases a type 1 error risk. So you have to be very careful when setting these things. Usually when we're talking about increasing power, we're talking about increasing sample size specifically. Okay. So to recap, when you're making or calculating the probability of making a type 1 or type 2 error, for normal distribution, your type 1 error probability is just your significance level. For a binomial and a Poisson, you need to calculate a CDF using whatever value you get for your null hypothesis as your probability or your lambda. For a type 2 error, you are doing a CDF. You are using a value that is given to you for your mean, your lambda, or your probability, depending on the distribution you're using. In order to reduce a type 1 error, you're going to use a smaller significance level, but be careful because that could increase the probability that you make a type 2 error. In order to reduce a type 2 error, the easiest way is to use a bigger sample size. However, again, this could increase the probability that you make a type 1 error. At the bottom, there are 3 problems that you are going to do, one on normal distribution, one on a binomial, and one on a Poisson. All of the answers are at the bottom.